So let's welcome to this afternoon's theoretical computer and information section. And we are welcome to Dr. Zhang from Microsoft. And today he will give a talk regarding learning with different privacy.
Thank you. Yeah, thank you. Yeah, good afternoon, everyone. So, today I'm going to describe this paper, Deep Learning with Differential Privacy. My name is Zhang, so I work at the Microsoft AI platform based in California. And this is a joint work with multiple people: Martin Abadi, Andy Chu, Ian Goodfellow, Brandon McMahon, Ilya Mironov, Kunal Tawar. And this was done when all of us were at Google. And this paper was published in 2016. The main work was done in 2015. So before I start, I'd like to thank the ICBS organizers again. So it has been a great honor to be here, a great opportunity to meet many people and also to share my work. So, which way? Okay. So before I get into the work, I'd like to describe what's the problem we are trying to solve. So again, I'm going to start with this simple example where the task here is to recognize handwritten digits. Right? So basically, there are a few examples here. This is a very easy task for human, and of course, we like a computer to do it. Right? So this is really old problem starting like from 1960s. So the way this is done is you basically digitize your image, you create a vector or a bunch of numbers so that your computer program can read. Then you can hire some kind of clever, smart engineers to write some program to try to detect the features of all this input image or these pixels, and then hopefully you get your answer. Right? So this kind of paradigm has been there for a while, like for almost 60 years. But this has changed in big way recently, right? So now this program now has been replaced by a function, a continuous function. Now, of course, the main one is a neural network. What kind of network it is less important, but this thing basically can be parameterized by a bunch of weights. So the way now you kind of write your program is you're not going to hire a software engineer to write the program or set the weights for you. Right? What you are going to do is you are going to hire some people to write some digits for you. Or maybe you can just buy some, or you can just get some from the internet, what we call this kind of data, training data. Right? Then you can set these weights by trying to fit these weights to your data. Okay, how is this done? So given any particular set of weights, right, then you can have a well-defined function. Then from that function, you can compare to its true neighbor. Then you can define some loss function, depending on how bad it does its job. Then your goal is, of course, just sum all the possible loss of all your data, and you try to minimize this loss function. Right? Then you get your weights. Once you find these weights, you can just happily use it to recognize digits. So of course, this can be a very complex function. It's usually impossible to find a global minimum. So what you usually do is you can just find a local minimum through gradient descent method. So I will come back to some details later. So this paradigm has had a great success. I probably don't need to say. So there's lots of sense now. We can even say there's a possibility to achieve so-called AGI, like real intelligence. I actually was truly inspired by Andy Yao's talk on Monday. Right? So if you have been there, I mean, even Andy Yao thinks this is great. I think this cannot be wrong. Right? So why it works, we don't know. Well, I don't know. Some people may know. I think it's still largely a mystery why it works. But we know what has caused, to make it a success. There are at least three reasons. One is there are clever people who have discovered some very effective domain-specific neural network architectures. The second one is because those kind of training requires lots of computation. So it requires hardware accelerator, which can do massively parallel computing. Of course, the third thing is basically a fuel to this kind of paradigm. That's training data. We need a large amount of training data so that we can train a good model. So since those training data are usually generated by individual users, so this model actually can have a risk, a privacy risk, because it does not only just do what it's told to do, it's supposed to do, to basically to recognize digits. It actually can memorize what has been used to train this network, right? So this has been demonstrated in multiple ways. So for instance, the first one, you can easily infer whether the data is in the training data or not. Why? Because since your model has been used to fit those data, so it will show different properties on this data it has been used to fit on. Then in this data, it has never seen. For instance, if your model is kind of overfitting, then its test accuracy will be higher than, the training accuracy will be higher than test accuracy. So on average, you will see better accuracy score on the data in the training data. So it's very easy. And people have demonstrated that to infer if given a data record, whether it's in the training data or not. So if you do have access to the model, like internal model, it's also possible to actually reconstruct some training data, right? So again, people have shown that if they can access the internal nodes, for instance, they can just try to construct the input, which can maximize some activation of some internal node, then that can give a pretty good image. This is original image. This is kind of what they have reconstructed from the neural network. Maybe you will say, oh, what's the point? I mean, since I'm doing a face recognition software, then it has to memorize how this guy looks like. But you probably shouldn't need to know all the details, right? So in which situation this image has been used to train this model. So more recently, so those generative large language models, people have shown that they are also very vulnerable to those kind of training example reconstruction. So Carnegie in 2021, a few years ago, they just showed that they can just craft some clever prompt and to force GPT-2 to spill out some kind of training data which only appeared once in the training data set. They actually, I think they have successfully reconstructed about 604 of them. And this is one example, right? So as you can see, this is really non-string, and it can be your kind of secret, your password. I don't think it's a password in this case. It's probably some kind of unique ID. So what's the big deal here, right? The risk, of course, one apparent kind of problem is if somebody got hold of your private data, they can use it to against you. They can target you, right? So if you have a medical record that gets into this bad guy's hands, they can use it to target you, to sell you like bad drug, fake drugs, stuff like that. They can scam you. They can even incriminate you, right? So another kind of reason that privacy is important is actually deep learning relies on user data. Right? So if people are there, they know if their privacy cannot be protected, they will be hesitant to share their data. But at the moment, especially public data is almost exhausted, right? So in the future, to keep driving this this progress, we probably need some kind of inner data, people's private thoughts, right? To have permission to learn how to think. So then in that case, the privacy is super important, right? Let's say if Elon Musk gets his way, he's going to put stuff into your brain, right? It's bad to be all this inner working in your brain to be protected. So then there's this whole field of so-called privacy preserving data analysis. Basically, so they ask this question, right? So can we harvest the useful information, aggregated information, or common wisdom from a large amount of user data without leaking individuals' privacy? Right? So now I'm using this word like privacy here multiple times already. What it is, right? So if you want to protect the privacy, first we need to have a way to quantify it so that we can measure it. So privacy is not new. It's probably we, as human, we probably have privacy from the very beginning. And of course, computer or internet has made this more prominent problem. People in computer science have tried all kinds of approaches to try to define the privacy. So I would say before, okay, you probably know I'm going to use differential privacy. Before the definition of the differential privacy, they have multiple attempts. So they all have this or that problems. I will just give you some examples. One approach is called anonymization. Take your data, I just remove so-called the PII, personally identifiable information. What it is, it's not that well defined, but it's intuitive, right? Like things like your name, your birthday, your address, this kind of stuff, which can link to you. Maybe we can just keep what kind of the books you have bought, what kind of coffee shops you have been to, right? Those kind of probably not so PII. But of course, non-PII can be used to identify individual too, right? If I follow you for a day, maybe I know which coffee shops you are going to go to. Then you can still use the information to identify you. So the second approach is let's just only answer questions if there's lots of people satisfy this query, right? So if they ask certain, how many people who go to certain coffee shop at a certain afternoon, then I find, oh, what's the average age, let's say. If I say, oh, I only answer this query if at least 100 people have been there, then I compute average age. So for sure, I don't reveal your privacy. But the problem is, if they ask this kind of query multiple times, they can do some subtraction, do some computation to figure out your private information, although every query's result is large set. Right? So third approach is let's just auditing it. Let's say I'm kind of the owner of the data set, then I just try to simulate you. So let's say if you want to ask this kind of queries together, they can leak somebody's privacy, then I just refuse to answer the second question. But of course, the problem is you don't know what the adversary knows, right? Especially the side information they know, they can use that to go against you. So as we will say soon, differential privacy is actually a robust notion which actually can get around against all these attacks. So before I get into the definition, I need to do a setup. So here is kind of what we have is a database. A database is nothing but a set of things, right? Set of records, and here each record corresponds to a single user. And then there is something we like to compute over this database, which we call query. A query basically has some range or output space, can be a number, can be a bunch of numbers, can be some combinatorial object, whatever. And then we have something called a mechanism. Mechanism is just a randomized algorithm which also gives output in the same space. It's just something which attempts to answer your query. So then the probably most important notion is this thing called a neighboring database. If we take a two database, basically two set of records, if we say they are neighboring, if they differ by exactly one element. Right? So basically, one set has to be just other set. You take the union with another data item, which is not in the set. Okay, this is kind of the setup. Then this is a definition of differential privacy. By the way, this is defined by Dwork, McSharon, the same Smith in 2006. I think they have the first initial definition, and which gets maybe refined or renexed by the other people, but I think it's they are commonly regarded as the inventor of the notion of differential privacy. So now, given all the setup we had, we call a mechanism is absolutely differentially private if for any two neighboring database and any O in the output space, the chance this mechanism on this two neighboring database that cannot be differ by too much, like the ratio. Right? So it's a very simple one-line definition. So why I say it's very robust against all this attack, we'll get to that later. So turns out this kind of the first definition, original definition, is also called pure differential privacy. Sometimes it's not too easy to work with. So there's also a notion called approximate differential privacy. basically, intuitive is just as, I mean, it has some definition, but intuitive is just as, except with a very small probability, and this probability is over the output of over some data set. Right? So it has to satisfy the differential privacy, the pure differential privacy notion. Okay, so this is a more kind of easy to work, flexible notion which I will stick to in the rest of the talk. And here, this epsilon delta, it basically measures how much privacy has been leaked. So which is also typically called a privacy loss or privacy budget. And epsilon is to be a small constant, and the delta needs to be vanishingly small with respect to the size of the database. So any questions so far? Okay. So as I said, this definition is robust against all this membership attack, even assuming F3 has access to all the data and setting information. Right? So here in the definition, there's nothing to say D is not known to the adversary. It says for any D and D prime, right? So the output of the mechanism cannot, the chance you get this output cannot differ by too much for two neighboring databases, right? So therefore, if you just take a D and a little d, which is not in the capital D, and if you don't know if which case the mechanism has run over, and you take the output, then there's always an uncertainty. You cannot determine which is the case because there is a bounded ratio between this probability. Right? Does it make sense? So another thing easy to say is if the adversary has set information, it will not help them because let's just imagine you just append a lot of attributes to each record, right? Let's say some set information you bought from somewhere. Since the mechanism didn't even look at this information when it's run, therefore after adding those records there, extra information there, so the output is still differentially private. So that's why the set information will not help you. So another very useful property, because this definition is so robust, so if you adaptively compose multiple differentially private mechanisms, it's still differentially private. Of course, the cost is going up, but that growth ratio is like a square root of k. So it's sublinear. By the way, this adaptive composition is that if you run this sequentially, and you can choose for the later query, each query can depend on previous result. Right? So this is a very, very useful property. So now given all this setup, now the whole work about differential privacy is really given only some query function Q, or can be some individual one, or can from some class, then given some privacy loss budget, how can we design a mechanism that is within the given budget, not privacy loss budget, and can return the most accurate answer. And this accuracy can be defined by whatever way as a downstream or as the application wants. Okay. So how do we achieve this differential privacy? So basically there are two kind of recipes. So first one is about the primitive. So if your query is simple enough, here is how you can achieve it, right? Now, here let's assume that the out space is some real space, is some k-dimensional space. Basically, you just ask k-parallel queries to this database, right? So let's say how many people in certain coffee shop, how many people in all the coffee shops in, let's say, somewhere, and you can ask all these queries, then basically you get some real numbers like a vector. So in order to make your answer differentially private, the first thing you need to figure out is the so-called sensitivity. So basically you want to know when you change one person, you add one person there, how much they can change your answer, right? And this how much is defined by the L2 norm between these two answers, right? So let's say if the query is just like what I said about how many people in here, how many people there, then changing one guy, right, can only change the answer by at most one. because you're just one person. So if you have k queries, then L2 norm is upper bounded by square root of k, right? Because every entry is at most 1. So then in that case, the sensitivity is square root of k. Of course, if we talk about a salary or some other sense, then you may have different values. But now suppose you have figured out your sensitivity, then you can just achieve the differential privacy through so-called the Gaussian mechanism. You just take your answer, then you add a noise, which is kind of with a standard deviation proportional to your sensitivity. Of course, you need to also factor in delta and epsilon there. So to say why this is differentially epsilon delta differentially private, it's also easy because the Gaussian is rotation invariant, or you can project it down to one dimension. So you just need to analyze the one-dimensional case. So suppose you have your database at D, and the value of QD is like here. And if you change just 1%, then we know by the sensitivity, so the distance between these two is at most S, right, the sensitivity. And then since you added the Gaussian noise, you know that only the ratio will be good in the middle, but of course, the ratio will be horrible at the tail, right, because the Gaussian is rapidly decaying. So, but then you know, because the way this sigma is chosen, so this tail probability is at most delta. So that's why it's absolute delta differential private. So, okay. Now, this is primitive. Now, suppose what you want to run is interactive queries. Then if you want to apply the same like recipe, you want to compute the sensitivity of the whole process, you probably will get some horrible, like a very large value, then you will add too much noise to it. So, but then in this case, what we can use is the composition theorem. Basically, for each individual query, you just apply your Gaussian mechanism, but then you just account for the total loss through the composition theorem, right? So basically, you can have some program there to say how many times. I mean, for each query, you can even use different budget and so on. And then at the end, you can just compute the whole like so-called privacy loss through this privacy content. So this is actually, as I will show later, is actually pretty effective for neural network training. All right. So now I have talked about deep learning and the differential privacy. Of course, the next thing is to add the differential privacy into deep learning. So for that, I need to get into some details on how this neural network is trained. So this is the early slide I showed to you. I stopped here, right? I say let's just do gradient descent and find the local minimum, right? A good model. So how this is done in practice, this is through the so-called stochastic gradient descent method, or maybe it's variant. But basically what you do is you just initialize your weight into some random values, and then you run this in capital T steps. At each step, you would grab some random batch from your data set. Let's say it has some size m. Then you compute the batch gradient. So what's the gradient for each individual data? Basically, recall we do have a loss function. Then we just compute the gradient of the loss function with respect to the weight. Right? Then we want to go down this gradient direction to try to make that loss small. Right? Of course, we need to do expectation or this batch. Basically, this thing will be a good kind of so-called unbiased estimate of the kind of the true full gradient. And then once you've done that, you just take a small step along down the gradient direction. Right? You do this t times, then you just return wt, or when the loss is small enough. Okay, so of course there are all kinds of variants there. Some, you can do some pseudo second order kind of thing, but that's kind of the basic idea. Okay, so how do we make this procedure differentially private? Right, it's really easy. If you just look at this simple process procedure, then what we really want, where the kind of the private data is used, is when we compute the gradient. So what is a gradient? Gradient is just a vector of very high dimension. You can just think it's just a vector with very high in a very high dimensional space, and it's the number of dimensions is basically the number of parameters, right, in your network. So then we just apply Gaussian mechanisms there. So what do? We just first of all, overall, we need to bound the sensitivity because this gradient sometimes can go wide. So you don't want to just rely its upper bound. You probably want to bound it. That's what we call a clipping process. Basically, take a vector, the clipping to some bounded constant C is, if it's not L2 norm is already smaller than C, then I do nothing, right? If it's larger than C, I just scale it proportionally so that the norm is exactly C. That's the first step. The second step is basically we just add the Gaussian noise proportional to this capital C when we compute the batch gradient, right? So this individual step is differentially private, is kind of follows through our early kind of argument, because if you change one data point here, you can at least just change at most one vector here, right? And we know we have already bound each gradient so that its L2 norm is C, so we know that this group gradient here, the L2 norm, actually, this is expectation. Let's look at the sum. Okay, this is actually a very important point. So if you look at the sum, the L2 norm is the difference of L2 norm is at most one between two neighboring databases. Therefore, adding that much noise will make it absolute delta differentially private. Okay. By the way, this method is not new. We didn't invent it. So some people credit us as the inventor of DPSG. That's not right. So this actually already proposed in 2013 by Zhang, Chaudhuri, and Sawati. They actually use this. They did some experiments, and then later on, this method gets analyzed by Sandy Smith and Takata. They actually showed this can work for convex models. So what we are actually trying to do is just to try to apply this to deep learning, to neural networks training. So now let me kind of try to relive the moment when we started working on this, right? That was around 2015. So at that moment, I think deep learning was just starting off. We have seen it has shown like a great potential in many areas, image recognition, speech recognition, and it has made a lot of money for certain companies. It's basically starting to take off. We don't have AlphaGo yet. There's of course, no transformer, no ChatGPT, nothing, right? Also, by that time, there's this cool thing called TensorFlow is coming out. People are actually working on it. So then on the differential privacy side, so this is almost 10 years from its initial definition. I think there was quite a bit of kind of ramp up time, but it has developed into a very rich theory. It has shown connecting to all kinds of things. We also did some work show it has connection to convex geometry. It has developed into a very fascinating theory. And they start to have some industry adoption for reporting statistics. I think by that time, maybe Google is the only one who is using it inside their product, to report which sites you have been to. This kind of quite private statistics. Right? Apple actually will soon to do that with the iPhone, right? iOS, but not yet. And then there's no demonstration in deep learning. So business statistics is a great theory. People have developed lots of great theory, but people start to be interested in industry, to get interested in it, but really there's not much kind of practical system, real demonstration out there. So another kind of at a more personal level is a few of us, we used to work at an MSR where actually this whole theory of differential privacy was originated. So we actually moved from MSR to Google. So we have done some theory work in differential privacy. We're interested in deep learning, right? So looks natural. We should just, try to apply differential privacy to deep learning. Right? So our initial motivation was very simple. So we just want to say, let's take the DPSGD, let's do some empirical study, and say, how well it can do. So there's a few things we want to do. Is first, we want it to run on standard benchmarks. We don't want to run on some random benchmarks so that the results is more calibrated. And we want to implement this thing in kind of the latest machine learning platform named TensorFlow. So one thing we want to insist is we want to have rigorous privacy guarantee, because by that time, people did try all kinds of differential privacy to machine learning, but it's not very rigorous. For instance, people do things like they don't clip the gradient to bound the norm of each gradient. They actually bound the norm of the summation, right? So that's not right. And of course, privacy accounting can be run. They count the privacy loss of individual parameter, not the whole model parameters. So we just want to do some kind of rigorous experimental work. We are not exploring any new theory. We will be happy with any non-trivial results, and we thought at least we will learn TensorFlow, right? Which turns out not very useful now. So anyways, okay, so that's what we did. So we did the implementation, but very quickly we realized, so if we just take a standard theory, it doesn't really work. So first, there are at least two issues. The first one is the privacy composition theorem is too loose. So if we just apply, figure out all the constant in all this, the composition theorem, and then we end up with pretty large loss. And also for privacy accounting, constant actually matters. Right? So because any constant factor in epsilon will translate to, because the definition, the odds is exponential in epsilon, we'll get into basically some polynomial x for epsilon. So even we try kind of the so-called amplification by sampling tricks, we end up with pretty large loss, privacy loss for reasonable accuracy. So the other thing is actually it's pretty expensive. The computation, the gradient clipping, because we want to do it per example. That actually does not work so well with the kind of the batch computation in the TensorFlow training system, right? So it can slow down our experiments, so we cannot do lots of hyperparameter search. Another thing is it's difficult to run like a large batch size or large model size. So basically, we have invented techniques to deal with both problems. I will only focus on the first one, which I think is regarded as maybe the main contribution of the paper. So we want to make the privacy accounting. Okay, all things back then was, the privacy accounting is too loose. Let's make it tight. It's not about the techniques are kind of not good enough. Let's just try to say what the tightest we can get. So here, this is when this alternative view of epsilon delta privacy is useful. So we can define something called a privacy loss random variable. So basically, this variable you can just take you just treat. Okay, so you can just define the ratio as your like kind of the privacy loss, right? Then your privacy loss becomes a random variable, and it depends on which output you observe. Right? Now, the statement about epsilon delta differential privacy is just to say the probability this random variable is greater than certain value is at most delta, right? This is just look at like any concentration inequality, right? And concentration inequality typically is proved through considering higher moments of this random variable. So that's basically our aha moment. We said, okay, let's just do that. Let's just keep tracking of higher moments of this privacy loss random variable. Then we also, at prior, we don't know which moment to keep track of. Let's just track all of them, right? So let's do a range of lambda. Then let's just accumulate this until the end. Then let's pick the lambda, apply the Markov inequality, then to find the best lambda, which give us the epsilon delta, right? So, okay. 1, 2, 3, 4 to 128, whatever. Very high. Yeah. So then okay. So we applied this to our DPSG, the STD, right? So recall in SGD, there is a batch sampling process. So here we kind of change the fixed sample to Poisson sampling. Basically, we just say each time when we sample this batch, we include every data item with probability P. And the P is M divided by the size of the database. Right. Then through some coupling argument, so when we compare these two, there was a D and a D prime, compare these two distributions. So some common argument, some pseudo-convex property of this moment, then basically it gets down to basically worst case is when you have the mu0, which is a standard Gaussian syntax 0, and the mu1 is a mixture of two Gaussians. Right? 1 minus P, which is standard 0, and with probability is standard 1. Right? So this is actually intuitive because you can just imagine the coupling process where you already sample, let's say there's a D and a D prime. D prime has one more element, right? Then D. You first sample this batch B from D, and you sample the same batch B from D prime. Then the last decision you whether you include a little d inside this batch or not. With probability P, you will include it. With probability 1 minus P, you will not. Right? If you don't include it, then the outcome will be the same as D, right? Because the batch B prime is the same as B, but with probability P, you will include this data. Once you include it, the worst kind of it can cause, the damage it can cause is can only shift this by 1 because that's the sensitivity, right? So then now the so-called the moment accountant just need to track these two moments, right? So these are two concrete distributions. How do we do it? We can just do it numerically. So we just did some numerical integration and then find out the value. And it turns out the B is easy to do. You don't need to do any like numerical integration because there's a closed form solution. Because mu1 can be written in this way. You can just do a binomial expansion, and the high moments of Gaussian is well known. Then you can just write a formula, right? So one interesting thing here is actually we did our numerical computation for both A and B. And the B is easy to compute. There's a closed form. A is hard. We have to go through all the, I don't know, Gaussian quadrature or whatever, this method to do it. And what we find out is actually B is always greater than A. It's very curious. So what happened is we thought this must be true. We tried all kinds of combinations. That's always true. Then in the code we released, we actually only computed B. We didn't compute A. So, but then a couple years later, we actually proved that indeed B is always greater than A. So that was a kind of an interesting little kind of story. So once we done this computation, we just can compose them. And this composition, because we know every step, the randomness, they are independent. We can just, by independence of these random variables, we can just multiply these moments. And as I said earlier, we try for all kinds of lambda. Then we run at the end, we just pick the best lambda. Right? Then apply the Markov inequality. So with this, we actually got a much tighter privacy accounting. So here I'm just showing these two curves here. The x-axis is how much we run this. We fix all the other kind of parameters the same for these two curves. X-axis is just how long we run this, how many steps we run this the DPSGD. And if we only use the best composition theorem from the literature, even with the so-called amplification by sampling techniques, that's the curve we got. But through all numerical one, we actually got pretty low, right? So you can see there's a striking difference. So not only numerically, we actually also did an analysis to show we do get a bad bound. So we do save a square root of log T of delta factor there. So this basically is a win for both theory and in practice. Okay. So, all right. So this actually the idea we had, basically I think two ideas, which one is to use this moments, keep track of moments, take advantage of particular noise we add to the to the answer, the other idea is to use a numerical method to compute the privacy loss. I think both those ideas have been kind of extended or generalized by many people here. I just mentioned a few. Okay, before I do that, so epsilon delta differential privacy is great as an intuition level. It's easy to explain, just two numbers, right? Who don't like numbers? But they are too lossy because when you compose them, you have subsampling, then only these two numbers, you have to consider worst case, you cannot get a very strong result. So that you probably want to incorporate your differential privacy kind of notion such that it actually takes some kind of curve in mind, right? It's not just a number, it actually has some shape there. So that's actually what the CDP work, actually around the similar time we did our work, they actually propose, basically they consider the situation where your noise is sub-Gaussian. They show that with that you get a more tighter kind of composition. I don't think their notion works for subsampling or not easy to work with. Another very interesting development is by Mironov. He is a cause of the paper, and we also working on the moments accounting together. I think one thing he probably did that at the same time or before it. So he realized the moments, so-called the moments are content. What it tracks is actually a classic mathematical notion called a Rayleigh divergence. So sort of great, there's a name there. So let's just use it as a definition of differential privacy. So that's when he defined the so-called Rayleigh differential privacy, and he showed that this you can get a tighter composition. And some other also showed that you can also do subsample Rayleigh DP differential privacy. I think now that this notion is broadly accepted as a pretty good kind of companion or relaxation of the original differential privacy notion. And more recently, there's also Gaussian differential privacy by Dong, Ross, and Su, and they also won the FS Frontier of Science Award. Yeah, congratulations to them. So basically show that it's easy also, it's actually pretty easy to do composition with subsampling too. Okay, so that's kind of the work I would say related to what we have done, basically to motivate people to give more kind of specialized differential privacy kind of definition so that you can compose better, right, or on the subsampling too. So another kind of branch is about the numerical kind of approach, right? So the moments account still, there are many places to use because we just keep track the worst case moments at each step, then we just multiply them together. So there is actually tighter composition. You actually take the real distribution, you convolve it, gets a single huge kind of distribution at the end. Then you can infer the properties there, right? So of course, if you take the distribution itself, it's hard to do it. So what you do is you discretize your distribution and it becomes a discrete problem. Then you can just convolve them, maybe through like fast Fourier transform or other kind of methods. It has a high computation cost, so you cannot do very fine grades. So it's very important. You need to up and lower bound it. Right? So, and there's a sequence of work which can show, reduce the computation cost. This graph I took from Golpi et al.'s paper. Basically, just ignore the red curve. So basically, what their work, their computation is two blue curves. One is the lower bound, the other one is the upper bound. Basically, the privacy loss, or by the way, x is up, y is epsilon, right? The true privacy loss is here. And this is what the yellow is what the moments are content can achieve. But of course, one caveat here is they use the particular set of parameters, especially the sigma is 0.8, which actually is not recommended for DPSGD. I think I will probably talk about this now. Okay, I will talk about it later. So with all this, we have actually done, being able to, I guess, almost 10 years ago to achieve some non-trivial results on both the accuracy side and the privacy side for this standard benchmark MNIST. And of course, this has been improved by quite a bit by now. So I recommend this paper in 2022 which actually gives very good results on the other more challenging data sets like CIFAR 20. They list lots of interesting techniques. There's also historical kind of bibliographical kind of reference there. So if you're interested. So one thing I'd like to, okay, very quickly. So what's really important? So we have done lots of experiments with many kind of parameters. So there are all kinds of things you do, right? This is like a machine learning. You know, people, you try kinds of things. Then at the end, when you write a paper, you say, oh, I think this is important and it's supported by all like experiments, right? But actually what happens is typically after the fact. So, but okay. So my point is, I think more important thing is you need to know what are the things you can try. But there are two things I think is important, which we actually in one case we kind of know why. The other case was a surprise, and it has also been corroborated by our own work or some other people's work. So I think there's probably some truth there. So I'm going to talk about it. So one is you want to use large batch size. Right? The reason is if you think about that gradient thing, the batch gradient computation, the noise will be divided by the batch size because you are moving into it. So if your batch is larger, then the noise may be smaller because a batch is larger, meaning you're also paying more privacy cost. Therefore, your original sigma needs to be larger. But that actually cancels out with the so-called amplification by sampling. So really, you want to be in a regime where the amplification by sampling is perfect. It gives you a p factor, like a factor of saving. So that actually p needs to be large enough such that you can get that effect. So therefore, you need a large set. By the way, 1% of data is huge, right? Let's think about the real application. You may have 1 billion of training data. So like 0.1% will be something like a million, right? So it's much larger than you would do without privacy. So another one is actually large or more sophisticated model actually works better for privacy. This is actually was a surprise against our expectation. Why? Because if you look at the Gaussian mechanism, right, you bound the whole norm to 1, then you add this noise, which the norm is on average like a square root of dimension, right? So basically, it says if you really have a very large space, then you add too much noise, which is also intuitive. If my model is only have 1 parameter, I have 1 million people, then I probably can estimate this parameter very precisely. But the problem is, if you only have 1 parameter, you probably don't have a very good model. So this actually, in some way, was when we did our experiment. Actually, by that time was super surprising. When we increased the hidden layer number of units for MNIST, which is unnecessarily large, we don't see actual decay of the privacy. I mean accuracy. By the way, the privacy cost here is fixed. So that was super surprising to us, but we didn't get to the bottom of it. I think this, although also kind of corroborated by other people's study, I think this is still some mystery there. Now, what is really going on? I think it requires some more study. But these two facts together, they imply that doing privacy training actually is maybe a computation quality trade-off, because both of this requires more computation, right? You need a large budget size, you need a large model. So, of course, I'm talking about is your computation, your data is kind of sufficiently large. So therefore, perhaps privacy protection is a computation quality trade-off, which makes sense like at the philosophical level, right? Because if you can only get 3 bits out from some data, you probably want to spend lots of time to think of how to use these 3 bits or extract these 3 bits. Right? So, but anything involving computation is hard, right? So as we know. So I think this is the last the last real slide is. So if you think about DPSC, it's actually stronger than necessary. Why? Because we are actually making every intermediate gradient differentially private, meaning we can just publish all these gradients out without, so the privacy cost is as computed. So this is more than necessary because we only need the final model, right? So one natural question is, can we further improve accuracy or further improve the algorithm by if we can hide the gradients, right? So, but this is not a total loss because if we, let's say the noisy gradients can be used, let's say for other optimizers like Adam, right? So if, since we already made it differentially private, they can just use at whatever we want. We don't need to pay any extra cost. All the intermediate models, we can also use it to do some exponential averaging. We don't need to pay any additional cost. And another interesting thing, it can enable so-called federated learning, where each user don't communicate their data back to the server. They actually communicate the gradients with noise, right? So this actually can maybe, support some new paradigm of this kind of machine learning. Okay. So to conclude, I think DPSG, our main work is to show that it's a viable technique for privacy preserving deep learning against our kind of initial expectation. We did invented some kind of new theory, and we also learned how to use TensorFlow, which is actually not as valuable as we thought before. Now, it was useful for quite a while. Another important thing why DPSGD is, I think, today is pretty popular is it's actually simple. It's easy to audit, right? People can understand it. What I showed to you is everything. Like, it's all there. I'm not hiding any details. So, in my opinion, privacy is ultimately it's actually about transparency. So your value of epsilon delta is not that important. What's really important is I want to know who is using my data, how it's used, right? The transparency. So that's another kind of interesting point. How do you prove a differential? A mechanism is differentially private. Typically, you do it by proving it, because you need to describe it. So, anyways, that's some work we did on SGD, and from the recent work, I think there's this two-cent point. I kind of think is right. One is if you have a large data set for hard population, right? People, they have lots of activity. They are common people. Then privacy protection is likely computation accuracy trade-off. Right? So, but then you also have this tail population who does strange things, and you want this tail population to help each other. There, I agree that if you really want to protect the privacy of these people, then your model accuracy may suffer. But there, maybe we can compensate you from better semantic understanding, not through kind of user helping each other, which truly try to understand what's going on, for instance, through maybe foundation models. Okay, so that's all. Thank you.
Any questions or comments?
Okay, I did such a good job, I guess. Okay. All right.
So the bounds you get, the tail bounds you get using the moment method, how much better are they theoretically compared to the
theoretically? Yeah, I think I showed it bound. Let's see. Is this the one? Right. We do save a root of log t of delta compared to the kind of the best bound you could get without just through epsilon delta, right? Generically. Oh, empirically, yes, I think the constant, because you want to figure out this constant, it's brutal, right? Empirically it's pretty good. So I actually don't know the other approach. I don't see any theoretical analysis with those approach, whether they can achieve asymptotically better bounds than what we got, or it's more just about the empirical tightness. Make sense? So another interesting story is we actually come up with the theoretical bound first. We showed it actually can improve the theoretical bound, as you can imagine, right? Now, this function. So then the first thing we did is actually want to apply that theoretical bound. It still didn't, I mean, it's better than the other bounds, but it's still not as great. Then we thought, why do we want to do this detour? Let's just use numerical value. Of course, people have to trust our implementation. We release the code, so people have to trust the implementation. I think that so far it's considered to be solid, especially after we prove that A is smaller than B. So, yeah.
Any more questions?
Thank you for your talk. I have a broad and more general question that what do you think for man in the CS, the like Microsoft?
The hotspot.
Yeah, the hotspot and the truly demand in the like.
Yeah, it's
No.
well, I guess it's okay. So from a business point of view, at least the short term, you don't want to change because it will hurt your accuracy. Right? But there's several things are happening. Right? One is there's law, more rigorous, I mean, strict law in Europe for sure. I think in US, I think in California, there's some law too, and people they need to be prepared for it, right? So another thing is there are certain companies which actually use machine learning much more than some other companies. So using apply differential privacy for this machine learning heavy company could be a loss for business value in short term, right? But actually for other companies, it could be a gain because those companies, they don't use machine learning, they worry about the image, right? But now, since they have a differential privacy protection, then they can apply machine learning. Turns out, for those kind of companies, it's an opportunity. So without naming which is which. Okay. So the third thing, of course, I think the public, as not to like what I said, right? So I believe for many products I saw, it's really a computation accuracy trade-off. So it's more about certain companies, they have built a humongous infrastructure surrounding certain way of doing things, and this is super expensive to change it. Right? Not only infrastructure, people's mind, your code, it's about the willingness to change. I think the harder population can probably cover you most of your revenue. Right? So there's no reason people shouldn't do it, but perhaps it requires a new company to do it. If you ask an existing company to do it, because the whole thing, the whole business model, everything is built around a certain way of doing things, it's very difficult to change, or it's also very expensive or costly. Right? So to give you an answer, you probably, I think what's in your mind is we don't say it. I don't say it too, right? So what's going on, right? It's great. I mean, if it's true as what you said, why we don't say it, right? So I think it will take some willingness.
Thank you.
Any more questions? Okay, maybe I got a little
Okay.
one. You mentioned I wonder if there is already like some publications in regards to this.
I think there is a publication which actually show. I can maybe give you a few names later. I don't remember exact title. They actually show that Atom is useful for speed, not so much for the final accuracy. It actually can in short stuff. Kind of at the beginning, it can outperform SGD, definitely private one. But then, if we look at the end result, they are kind of will get to the same place. I think that's the kind of conclusion they got. But I know in practice, Atom is important for certain machine learning models. I mean with differential privacy.
Okay.
So.
Any more questions? Let's thank our